Thank you for taking time to watch the video. Today it's video 4 in our Circuit Protection Fundamentals series, Common Test Errors. We'll go over a few common test errors here. One is associated with current probes. Another, number 2, electronic loads. And our old friend transients from long supply leads. And number 4, supply I limit too low. That's an odd one, but we've gotten more than a few calls on it. So error source number 1, and I've been bit by this, is current probe behavior. Current probes are great tools. You can see the waveforms, observe their shapes, watch the current change, and you don't have to have an element in the loop. They just clamp around the cable. What could be easier? You don't have to cut anything. However, you have to be careful because they need frequent degaussing and calibration, especially if there have been large transients or current spikes going through them, which is quite common when you're doing hot swap and circuit protection testing. And they're not so great for really precise measurements. For getting relative curves and waveforms and understanding generic behavior, they are a very powerful tool. For making precision current measurements and measuring the accuracy of a current limit threshold, not so much. They have a limited bandwidth, so when we get a high transient, you can get misleading curves coming out of your current probe. And the accuracy is 1%, and that's at best. Here, we can see characteristics of a current probe. It's spec'd out below 120 megahertz, and our DC accuracy, and this is DC accuracy, is 1% typically and 3% guaranteed. And the maximum peak pulse current is 50 amps. If we're doing short circuit testing on a 20 or 30 amp system, it can easily exceed 50 amps. So they're a great tool, but you need to know their limitations. So what do we do for precise DC current measurements, in particular when we're trying to measure the accuracy of our current limit threshold? If the load is less than 10 amps, I use a multimeter. There are many very accurate multimeters out there which can give you 3 or 4 digit precision below 10 amps. Now, if the load is greater than 10 amps, and we have many solutions that are, then we'll use shunts and multimeters. And I will try and pick our sense so that the voltage across the shunt is anywhere from 50 to 100 millivolts at the I limit threshold. And if you're going to be measuring power dissipation, remember to measure the voltage for the power equation at the load, not at the source, because now you've got a voltage drop across the shunt. So here we can see for less than 10 amps, power supply, load, and a digital multimeter in series with the power feed. Over here on the right, for larger supplies or larger currents, we have a shunt, which is probably a few milliohms, with a digital multimeter measuring the voltage across the shunt. Error source number 2, electronic loads. Again, another very powerful tool. They're extremely useful, but they do have some limitations. And again, in particular, when you're trying to measure precisely a current limit threshold and creep up on that current limit, the electronic loads are perhaps not the best solution. They're great for DC loading and automated tests. It's very important to have proper setup. There are many modes on here. You can set up an electronic load to either provide a constant current load, in which case it will always try and draw whatever current level you have asked from the source. Constant power load, where it will always try and draw the same amount of power from your source. or the constant resistance load, where it just pretends to be whatever resistor you tell it to be, and it will present that resistance to the source. Unfortunately, when we try and creep up the current level by slowly increasing the power or decreasing the resistance or increasing the current being drawn from the source, there can be transients within the supplies as it switches, or within the load as it switches states and switches in new loads. These transients can actually cross the threshold, the current limit threshold, and cause a premature trip. And what you will see is an apparent current limit that is lower than what you expected. So what do we do? Well, method one, they laugh when I pull these out in the lab, but I know exactly what they're doing and I know how they behave. We get some big old resistors and we use that to heavily load the supply or heavily load the protection circuit and draw most of the current, maybe 80, 90, 95% of the current. Then we creep up that last few percent, we creep up to the threshold with a very fine wire wound resistor, or something where we have a lot of control and it's got a fine granularity with no transients. Another option, method two, can be used, which is set up a FET with a potentiometer and a shunt resistor and just use this FET to load up the supply or the protection circuit. But be careful, the FET can handle all the power you're asking it to handle. This circuit can also be used in parallel with big old wire wound resistors. Our next error source, long supply leads. All wires are inductive, and long supply leads can have significant inductance. Very often, somebody will take an EVM, put it on the bench in the lab, and then hook it up to the wires that are coming out of the back of the lab supply, and now you've got 2 meters of inductance hanging on your supply, and you may have another 2 meters of inductance off to the load. Ironically, this can be the most transient-prone situation for one of these devices, being in an EVM on the lab bench. In most of the applications, we'll see these protection devices with very short leads on either side of them, either to a backplane or to the load itself. So when the FET turns off, we get these large voltage spikes that are due to the inductance in the LDIDT. And to counter these inductive spikes, what we'll do is on the input to our control IC, we'll put a capacitor and perhaps a transient voltage suppressor, which is somewhat like a Zener diode. It will clip or clamp the voltage surge. And in the output, we can put a Schottky diode, and at shutoff, when a negative spike occurs here, the voltage won't be allowed to go more than 0.3 volts negative, because this Schottky diode will be forward biased and clamp that voltage. Many EVMs that we sell already have the capacitor, the TVS, and the Schottky on them. And we get questions from customers saying, do I really need that? And we said, probably not, but the EVM does, because we don't know who's going to hook it up with how much wire and to what type of supply. And twisted supply leads can also help cancel the inductance in the feed and the load wires. And this is a somewhat odd error, but it's happened more than once. We'll have a customer call up and say, well, I was running the test, I put a short circuit on it, and the FET blew up. It shouldn't have blown up. And they'll send us some waveforms, and we'll look at the waveforms and say, well, turn up the current limit on your power supply. I think it's set too low. And they'll say, well, it already blows up. Why is setting the current limit higher going to save it? And it turns out There are multiple turn-off thresholds and speeds within many of these devices. When we pull down the gate to turn off the FET, if we just disable it or deassert enable or turn it off, or if the input drops below the undervoltage lockout level, it turns off and pulls down the gate at about 2.4 milliamps. So now the external FET is having its gate discharged at about 2.4 milliamps. If we have a fast trip, because there's a giant transient or a short circuit, the gate is pulled down at 125 milliamps. And that's 50 times harder than it would otherwise be shut down. So when the supply limit is set too low, the short circuit drags down the output of the protection circuit, which drags down the input of the protection circuit, which drags down the supply voltage, and before the fast trip current can be reached to cause it to shut off, the undervoltage lockout threshold is crossed when the input voltage drops. And when that UV threshold is crossed, instead of dropping and pulling down the gate at 125 milliamps, we're only pulling it down at 2.4 milliamps. It turns off too slowly, the FET SOA is violated, and the FET lets the smoke out, and then we get a call. And it is always interesting when we say turn up the current limit on the supply, and they say it'll never work, but they never call back, and we find out from the field folks it in fact did work. So fix one, ensure the power supply is set to supply current well above the fast trip level. And fix number two, if you don't think your supply actually can supply that much current, for the purposes of testing, you can attach some large bulk capacitors right to the input of the device before running the test. And that will hold up the input supply and give it enough charge to allow the current to peak and cross the fast trip threshold. So trends we're seeing in circuit protection: more and more accuracy, more desire for power limiting as the currents go up, and more monitoring. Everybody wants more efficiency too. There's a lot of attention being paid to power dissipation. One of our customers is telling us that his customers will pay $12 to $18 for every watt they can get rid of in a large server. And that's the lifetime cost of a watt as their customers have determined it to be. So if we can lower our threshold voltages and consequently lower our cents, that saves them energy and operating expenses directly. We're wanting higher levels of integration, bringing the FET into the package, bringing the sensing element into the same package. We're seeing calls for more PM bus, I2C control, and again, this helps support intelligent power management, green grid, and smart grid. And we're seeing e-fuses replacing and augmenting regular fuses and polyfuses for a number of reasons, not the least of which are much higher accuracy and much lower losses. And within the PoE world, or power over Ethernet, traditionally the loads would be 13 watts, and then they went up to 25 watts. Now we're seeing demand for power over Ethernet for up to 80 or 90 watts. And that, I believe, is today's presentation. Thank you.